Hi guys, today's lesson is on solving exponential and logarithmic functions, part 1. We're going to continue with more complex logarithmic functions tomorrow, or in our next lesson. But first let's start with exponential equations. Just a review that these are equations in which variable expressions are exponents, and the property of equality for exponential equations basically states algebraically, if b is a positive real number other than 1, right, we can't have a negative base, then b to the x equals b to the y if and only if x equals y. So what it's saying is that 3 to the x equals 3 to the 5, then x equals 5. Let's shortcut all of that. If we have the same base, then we can solve exponential equations by setting the two exponents equal to each other. Okay, and this only works if you can write or rewrite each of the bases to be the same. So if the bases are the same or equal, then the exponents must be equal in an equation. So that's this first one. When it's not possible to write each side of an exponential equation using the same base, then you can try to solve the equation by taking the logarithm of each side. Both sides. But for this you need a calculator. Sorry about that. For this one we don't need a calculator. I'll show you an example of each of these below. Okay, so take a look here. We know this is 10 to the x. And this is another one that can be written as 10 to the negative 1. And so if the bases are the same, then the exponents must also be equal, which means that we then have x equals negative 1 parentheses x minus 3. And I can distribute and get x equals negative 1x plus 3. Add x on both sides, that's 2x equals 3. Sorry, and we get x equals 3 over 2. Now, if I wanted to, I could check this, because, I don't know, this looks a little potentially weird, and I don't know if I'm right or not. So instead of asking your teacher if you're right, you can do 10 to the 3 halves on your calculator and see if it equals to 1 over 10 to the 3 halves minus 3. And so this one we know is going to be a decimal answer because this is a square root of 10 to the 3rd power, which has no whole number answer. So I'm just going to write in 10 to the 3 halves. And then I have 1 over 10 in parentheses, please, to 3 divided by 2 minus 3. And, oh, something went wrong. I forgot my parentheses around my exponents. There you go, proving that those are exactly the same. Okay. Now, on the right side, if we have 2 to the x power equal to 7, I can not rewrite 7 as a base of 2. Like, it's not possible. I know it's going to be between 2 and 3, right? Really close to 3, because 2 to the 3rd power is 8. But what I can do then is take log base 2 of both sides. And then I'm going to squeeze this in, sorry, of that. Okay. So these two, the log base 2 cancels out with the exponent base 2. And I get x equals log, and this one I want you guys to be careful of. I did notice one person writing this slightly as an exponent. The log and the 7 are the same on the same line, and the 2 is down below. And then if I don't have a calculator, I would leave my answer as log of 7 over log 2. Right, because that's literally what I'm going to type into the calculator, so the argument over the base. But since I do have a calculator, you can also write ln 7 if you wanted to. But since I do have a calculator, I'm going to type it out and go log 7, close parentheses, divide by log of 2, and that is 2.807, approximately. Okay. If I don't specify what to round to, I usually just specify, like I usually don't write the whole number. That's my only rule, because then that shows that there's a decimal after. So how do we see exponential equations in the real world? Well, one of the most important applications is Newton's law of cooling. And this law follows this equation here, or formula, and it states that for a cooling substance with initial temperature T sub 0, or T naught, the temperature T after 10 minutes follows this, where TR is sub R is the surrounding room temperature, and R is the cooling rate, and there's a negative to show that we are decreasing in temperature. Okay, this extra comma, I'm really sorry, it doesn't mean that these are different. I was trying to continue my sentence where I talked about modeled by this, where, yeah, so it's poorly written. Okay, so you're cooking a licha, an Ethiopian stew. When you take it off the stove, its temperature is 212 Fahrenheit, which is the boiling temperature. The room temperature is 70 degrees Fahrenheit, and the cooling rate of the stew is at a rate of 0.046. How long will it take to cool the stew to a serving temperature of 100 degrees Fahrenheit? So let's take a moment. You actually don't need to understand anything except to plug things into the formula, and then solve for the variable that is left. Okay. So how long means I'm solving for t. That sort of just gives me an idea. So I want the end temperature. This is my end temperature, right? Is 70. No, the end temperature is 100. We started at an initial temperature of 212. The room temperature is 70, right? And so we're subtracting the 2 because we don't need to go past that. We're just trying to find out how long it takes to for it to cool by the difference in that. Let's see, times e to the negative 0.046. T, we don't know, and then plus room temperature is 70 again. Well, at this point, we're literally just solving for t. So we're going to move things around following our Algebra 1 basic rules of whatever stuck doesn't get solved until later. So we're going to follow our steps. The outermost things go first. This will be 30 equals, and I can subtract that right now. It'll be 142 times e to the negative 0.046 t. Okay. At this point, I'm trying to get this by itself, right? E to the something power. So I need to divide by 142. I'm not sure what it is, but I think the chemistry, I loved AP chemistry, and I could be a chemistry teacher, but that teacher in me makes it so I don't want to deal with decimals. And my teacher in chemistry always taught me, like, whatever the fraction is, just leave it until the very end. So I'm going to leave this as 30 over 142 equals e to the negative 0.046 times t power. And how do we get rid of, well, t and negative 0.46 is together. How do I get rid of the e? The inverse of e is ln. So these cancel out. And then I have now negative 0.046t equals ln of 30 over 142. Okay, we're getting really close. The last thing to get t by itself is to divide. Negative 0.046. And so I get t equals ln of 30 over 142 divided by negative 0.046, which is approximately, if you type into your calculator, 34 minutes. Like I said earlier in class, if I don't tell you what to round to, I cannot take points off if you round to something different, right? So whole number doesn't hurt. I don't know what 0.8, I think when I did it on my calculator it was 0.8, and I don't know what that is. So to me, I stopped there because 0.8 of a minute meant nothing to me. That's why I didn't round to 33.8, because it was useless. Okay, there we go. Moving on. I have 3 practice problems for you guys to try. Okay. I'm going to pause the video here so that you can take a moment to try this yourself. Okay, you have to show your work. I'm not going to show my work for this, but you guys are responsible for doing it. Okay. Okay, so here are your 3 answers. Please check, always recognizing that I might have made a mistake, but I did do it, I hope, correctly. Logarithmic equations. So now we're moving on. These are equations that involve logarithms of variable expressions. So the variable is in the argument. And the property that we're going to focus on here is exactly the same as the property of equality for exponents, but we're going to translate that to the property of equality for logs. So it's saying here, long story short, same as before, if the log bases are the same, right there, then the arguments must be the same, right? Because we start with an equation. So if log 2, log base 2 are the same, then x must equal to 7. And so this states that if you are given an equation, or implies x equals y, log of something equals log of something, you can do this thing called exponentiate. Oh, that's this one. Sorry. Let me jump here. We'll do this one first. Okay, property of equality. So all this is saying is that now we have 4x minus 7 equals x plus 5, right? And we can solve it. So that'll be 3x minus 7 equals to 5, 3x equals 12, and x equals 4. If we plug it in to check, we're going to get ln of 4 times 4 minus 7 equals ln of 4 plus 5. And that'll be ln of 16 minus 7. Check. Okay. So now let's take a look at what if the log bases are not the same on both sides. Well, there's no way we can get a log base 2 of 3 somehow in our head. So we're going to exponentiate each side only one time each. So what this means, if there's like 2 logs on the left and 1 on the right, we cannot go inverse operation like all 3 of them by doing this base 2 right there. Okay, because the inverse of a log base 2 is an exponent base 2, and then that will give us, like at a certain point, b to the x equal to b to the y, right? And this technique is useful for solving sum. Okay, tomorrow we're going to see when does this not work. So if this is gone, we have 5x minus 17 equals 2 to the 3rd power, which is 5x minus 17 equals 8. So just be careful, this is not 2 times 3, it's 2 to the 3rd power. This will be 5x equals 25, and x equals 5. If I plug this back in, I'm going to get log base 2 of 5 times 5 minus 17 equals 3. Now notice when I checked, I did not do inverse operations, because if you made a mistake here using an inverse, oh, I'm so sorry, making an inverse operation, then you might make the same mistake over here. So now I'm going to just simplify what I see. 25 minus 17 equal to 3. And this is 8. And I can simplify this by writing as log 2 of 2 to the 3rd. So 3 equals 3. Okay. So to wrap this up, we're not going to do another problem that this applies to, but let's talk about domains a little. One thing to remember is that while exponential functions have a domain of all real numbers, okay, logarithmic functions only have a domain or x value of half of the domain, either greater or less than the asymptote. right? So the graph only shows up on like half of the, so the function shows up on half of the graph. Since this is always the case, you need to always plug in or check your solution to verify that your solution lies in the domain of the function. So when checking, you do not use inverse operations, like I said above. Instead, you are simplifying each side. Now, for logs, it's actually a lot easier than doing this. We're going to assume that this is always correct. But as soon as you see, like if something happens in between where you end up with a negative argument, so if the argument of the logarithm is negative, you can eliminate it right away and say no solution. So if I get log base 2 of -8, immediately I can say that we're done and there's no way for this to work. Okay, so but I would want to see it, and then you would write not possible or no solution and cross this out. That's going to be our next lesson, just a preview.